Formulas. We have a bunch of formulas. These are the set of formulas from last time. Did we start a problem last time, or? Oh. We did, huh? All right, let's find that last example. Oh, here it goes. Okay, so we must have been trying to find the center of mass. We're going to find the mass, and then we're going to find some other stuff. Oh, so I think we were on our way here to find the limits for x and y to set up our integral. So we're going to find our x values. So let's see, these parabolas, y is equal to x squared, and x is equal to y squared. And for some of these, we want to express it in terms of x. So for this, in terms of x, we would take the square root. That would be square root of y, and just the positive part, because the negative part is over here, and we don't really care about the negative part. And then your other function is just y squared. And you go into the function via this square root of y. So your limits are going to be going from square root of y to y squared. So you make your slices starting when x is equal to, or when y is equal to 0, all the way up to y is equal to 1 with constant limits. Okay. So this is going to be your limits, and this is going to do one integral to find your mass, and you'll get a value for your mass, and then a couple more integrals to find the moments with respect to x and y, and then divide it by the mass to get your center of mass. So let's find the mass. M is equal to some double integral generically over the domain or the region of the rho function. Okay. So the working definition now, rho is equal to 11 square root of x. I suppose we should have taken the 11 out and written x as x to the 1/2. We're going to integrate with respect to x first, and that's going to go from square root of y to y squared, and then we're going to integrate with respect to y from 0 to 1. So we can't take anything out. We need to do this integral first. X to the 1/2, x to the 3/2 divided by 3/2, so that's 2/3 times 11, x to the 3/2 power. And then you need to evaluate this because your x limits are going to go from square root of y to y squared. So you need to evaluate this from y squared, square root of y to y squared. So if you put y squared there, you're going to get y cubed. And if you put square root of y there, you're going to get y to the 3/4. Is that correct? Hope so. And then you're going to integrate this from 0 to 1 with respect to y. So 22 over 3 is constant. And then you integrate this, you get y to the 4th over 4 minus, and then you add 4/4, 7/4, y to the 7/4 divided by 7/4, or multiply it by 4/7. And when you put 0 in, everything disappears, so it's just putting 1 in. 22 over 3, 1/4 minus 4 over 7. Oh boy. -28. -9 over 28. And then the 3's would cancel, 2 would cancel, 33 over 14. Negative. Oh. I don't know if we should have a negative density or mass. All right, find my mistake. Where? Say it again? Did I switch them?
When you say square root of y is less than or equal to x, less than or equal to y squared, for when y is between 0 and 1, the y squared is less than the square root of y?
I think that's what James was saying, but I think if we draw a line parallel to the x-axis, oh, yeah, you're right. So I got these two things switched. Yeah. Sorry. Is it? Yeah. Yeah, so going in here, this is the first function, and I think I put the arrows in the wrong place. And this function over here, maybe I should have done different colors. This should be the lower function, which is y squared, and then square root of y is the upper. That would do it. All right. Can we just switch it and put a negative in front, and is it going to work out? Track my mistake here. Y squared, square root of y. Y squared, square root of y. And so these two are switched. what did I just erase? Y to the 3/4 cubed. And so these two are switched. Four over 7 y 7/4 minus 1/4 y to the 4th. And then that would just mean that these two numbers are switched. And that would mean that this would be a positive. Okay, whew, that's better. So the mass is 33 over 14, whatever units they are. Doesn't say. Grams, kilograms, kilograms. Now we need to find the center of mass. Now it's always kind of tricky for me because I can't really remember what x bar is equal to. So I know it's divided by the mass, but the moment, I think it's y. It gets switched. One of them gets switched. And the moment with y is a double integral over the region of the density function times x. You know what? We have a list of formulas here. Oh, it's my, and then my has an x in it. Those physics people. Has an x in it. So then your integral. So the nice thing about this is that we have basically our integral set up. We just have to do another integral where instead of 11x you would have x times 11x, or 11 squared of x. And you can use the same limits. And so this integral is going to be almost as easy if you do it correctly. And then instead of x to the 1/2, you'll have x to the 3/2, and then you carry on with the computation that way. So instead of me having to do all that, I'll have Mathematica do it. Right? Yep, that's right. Go from 0 to 1, and then another integral, this time going from y squared to square root of y. And I have 11 times x to the 3/2 power. Whoops. So 11 over 9 for that one. So if this is 11 over 9, then your x bar must be, what was it up there? 33 over 14 divided by 11 over 9. Let's see, reciprocals, 3, 9, 27 over 14. What? Oh, backwards. Yeah. 11 over 9 divided by 33 over 14. So, what is it? Try and do it in my head, and my head's getting tired. 27 over 14. That doesn't look right. 14 over 27? So I say 27 over 14 doesn't look right because it's bigger than 1. And according to this graph, the surface, or the lamina, the plate, your X bar and your Y bar has to be in that space, right? And so if your X is bigger than 1, then you know you did something wrong. If your mass is negative, like we found it to be negative, then we did something wrong. So want to make sure that our answers make sense, and our answer for X bar has to be between 0 and 1. Same with our Y. Should also be between 0 and 1. So let's find Y with the help of Mathematica again. So Y bar is equal to the moment in X over the mass, where the moment in X is equal to this double integral from 0 to 1, from Y squared to square root of Y. This time it's Y times 11 square root of X dx dy. Okay, so I'm just going to go ahead and punch that into Mathematica. So it's Y times 6/5 which means Y bar is going to be equal to 6/5 divided by 33 over 14. So you do that reciprocal thing, you get 28 over 55. Good. It's a number between 0 and 1. So if you were to take a look at that plate, 28 over 55 and wherever that is, and 14 over 27 wherever that is, if you just suppose if you punch it in your calculator, you're going to get a decimal approximation that would give you a clear idea. 14 over 27 comma 28 over 55. That would be the balancing point of this plate, which means if you lay this plate onto this point, then it should be able to balance itself. Okay? Any questions? So these things, I think it's just a matter of using the formula correctly and making your calculations correct. So for your homework, you do these calculations. In an exam situation, I probably, this is probably about as hard as it gets in terms of the integral that you have to compute. I'm going to not have you compute, have you try to use integration by parts or partial fractions or things like that. And if you are to compute anything like this, I'll probably just ask you to punch it in your calculator. Although this is a double integral, so you have to take one first step in the calculation to pare your integral down into 1 instead of 2. So, but most of the problems that I'll be asking you will probably just be setting up the integral without having to compute it. All right. And like I said, I'm not very interested in the second moments, the inertia stuff. But if you want to take a look at that, you can. Well, you'll probably have some problems for homework with that. So that would be just good practice for you to be able to do. But in the exams, I'll focus more on the center of mass. Okay. All right. The other. Oops. The other application I was interested in doing was probability. There's some basic probability I think that would be good for us to know. You guys will be dealing with, I'm assuming in some physics or engineering classes, you guys will probably be dealing with some probability density functions. And the probability density functions are extensions of the regular density function in one variable. And it starts off by a couple of properties for your function. And if you have a function that's supposed to be a probability density function, then the area under the curve of that probability density function has to equal to 1, which means the heights in any of those is less than 1, but it's also positive, so it's bigger than 0. You don't have a probability that goes below 0. That doesn't make sense to have a negative probability. How many people have studied some form of statistics where you might have talked about the bell-shaped curve? Okay. So the idea behind a normal distribution the standard normal distribution is a bell-shaped curve that goes infinitely forever, and it's some function. I'll put a star there because I can never really remember. And some more stars there that I don't remember. But it involves e to the negative x squared. So the general shape of e to the negative x squared is the bell-shaped curve. And then with the appropriate constants in front and constants that's around the power, they make it into a probability distribution. And the idea is that this is all positive, it's above the x-axis, and the area under the curve is equal to 1. So given that the area under the curve is equal to 1, in statistics we often have problems like, oh, what if you want to go from A to B and you want to find this area under the curve from A to B? And so in calculus we would integrate that, and then we would, that value that we get here, the area, actually corresponds to the idea of a probability. ability. Probably misspelled that. So, for example, if we say that the men's height is, I don't know, 65 inches, average height of males is 65 inches with a standard deviation of, I don't know, 0.6, 1.2, something like that. Then we can ask, if you randomly select the guy, what's the probability that his height is between 6 feet or 60 inches and 63 inches? And so in answering that question, you would refer to a probability distribution like this, and then you would find the area under the curve. And in statistics that we teach here at Cañada, we pull out our calculators, and we have a special command for that called the normal cumulative distribution function. So all right, so that's the one variable equivalent. But now you might have a probability distribution that relies on two variables. And so your probability distribution function would be f of x, and that f of x has to satisfy these two criteria, that it always has to be bigger than 0 in its domain, and the probability of this distribution over all the possible values that we could put in for x and y is going to have to equal to 1. And then after that, you can find the expected value, or the average in the x and in the average in the y. So if you look at this, kind of should give you some flashbacks. Sort of. Because it looks like the center of mass, right? So the idea is that you would divide by the this is like the first moment in y and the first moment in x. And then you would divide by the mass, but the mass is equal to 1, so it really is just like the center of mass. In fact, x bar and mu are the two symbols for the average, the mean. So it's really just the special case of the center of mass where the whole distribution, or the mass, is equal to 1. All right. Now that I threw all that out there for you, we can try to do a problem. And just so this might be a little clearer. Let's do number 28. We can do 28 or 29. Yeah, 28 looks easier. 29 looks like it's an improper integral. If you look at number 28, it goes from 0 to 1, 0 to 1. So, and then the 0 everywhere else just means we can ignore that. We can ignore everything, and so this kind of sets us up for our domain. Number 29 says x is bigger than 0, y is bigger than 0. Well, that's the whole first quadrant, which means it goes on to infinity. So number 29 would require an improper integral And the improper integral, I think you can be okay with this improper integral because this is an exponential decay in both the x and the y, so you'll see it that it's actually going to be finite. I don't want to do an improper integral, so I'm going to do the other one. So here we have a function that's defined piecewise because of the zero business. And the first thing they ask us is to verify that it is a density function. So just by inspection, you can see that, maybe I should actually write that down. By inspection, that if we put any numbers in the first quadrant square from 0 to 1, 0 to 1, any of those numbers, that we're either going to get 0 or something that's positive. Okay, we're never going to get anything negative. So that's the first part that they're asking for. The second part is that if we integrate over the whole xy plane, that's all of R2 of this function, we want to know if this is going to equal a 1. So that's what we're going to check for. Well, when we integrate, we're going to have 0 for all kinds of other places in a domain except for when x is between 0 and 1 and y is between 0 and 1. So immediately, this is kind of like your domain that we can deal with. So this integral here will actually equal to the double integral, and I don't have to write this out in inequalities because it's already written there for me, of the function for xy, and then dx dy, it doesn't really matter which way I'm going to integrate because the integrals are constant. So I'm just going to go dx dy. Dx goes from 0 to 1, and then the y goes from 0 to 1. Okay, now we'll do this integral, constant limits, and they're separable. I mean separatable. I don't want to say separable because that's a differential equation term. So we'll separate it. I mean, you don't have to because it's just as easy to do. But to me, saying integral of x from 0 to 1 is a lot clearer because that's just 1/2, right? So it's x squared over 2 from 0 to 1. And then we have y, the same thing, so that's also 1/2. And this, in fact, is equal to 1, so that checks out. So that's part A. Part A, we verified that it satisfies the two properties for a probability density function. Part B, x and y are random variables whose joint functions are a function above. Find out when x is bigger than or equal to 1 or 1/2. So we didn't draw the region in the domain, but we'll do it now. So this is the region where the graph exists, and everywhere else is equal to 0. So we only need to consider this as its domain. And now they're further giving us more restrictions. And to find this first one, the probability where x is bigger than 1, what they're saying is that they don't care what y is equal to as long as x is bigger than 1, or 1/2, sorry. Now we just trimmed down our domain from that square to a smaller rectangle over here. And then we can set up our integrals here where we say, well, our x goes from 1/2 to 1, and our y still goes from 0 to 1. So all we have to do is do an integral with this as its domain. So the probability where x is bigger than or equal to 1/2 is going to be given by a double integral over this domain. Let's call this d1 of your f function. And again, this will have constant limits. Our f function is 4xy, and our x goes from 1/2 to 1, and our y goes from 0 to 1. So it's essentially the same integral, except you have slightly different limits. Okay, so I think a good strategy for this is to draw your region. In this first one, I didn't have to draw it because it seemed painfully clear, but if it doesn't, then you should draw the region here. Draw the region for the probability that you're looking for. Okay, so I'm not going to integrate this. I'm just say dot, dot, dot. And then the next one, the probability, this is part I. Mm-hmm. Yep.
That just means given this population.
Yeah, given whatever this is. Whatever this problem is. I'm trying to think. I can't think of a relatable example for this problem. The other one I could. It's like your stereo. The time that your stereo would, require a warranty or something. What's the probability your stereo is going to break down from a certain amount of time to a certain amount of time? Anyways, if you were to do a graph for this one, this one is looking at where x is bigger than 0. So I'm going to do this in two different colors and combine it. So x is bigger than 1/2. Sorry, x is bigger than 1/2, and then y is less than 1/2. So this is y less than 1/2. So the question is where they intersect. Wherever they intersect is going to be your region. So they actually intersect in this little square region over here. So then you would set up your limits accordingly. Your x looks like it's going to go from 1/2 to 1, and your y looks like it's going to go from 0 to 1/2. So you just set up your integral the same way. So x goes from 1/2 to 1, and y goes from 0 to 1/2. Okay, just a bunch of plug and chug formula things, so you just have to be able to interpret the problem. All right, the last one is to find the expected value of x and y, so the averages, the x mean and the y mean. I'll do one of them. Well, I'll start one of them. X mean. A formula says that you're going to take the double integral over the whole plane of the function times the function times x. X times the function. Okay? So that is going to be similar to this problem that we just did up here. So mu sub x is going to be equal to this double integral of x times 4xy, and you can combine that to 4x squared y. Dx, dy, x goes from 0 to 1, and y goes from 0 to 1. And then, so this would just be as easy to compute. Now, the only thing that you should worry about is that whatever answer you get here, that number should be between 0 and 1, because that's where the domain lives. Your mean should be between there. And it's not necessarily right smack in the middle, because this is, it's not a plain uniform function. Okay? So a couple of things to just think about. Probabilities. So these are probability questions. And after you calculate this, you should get an answer between 0 and 1, because probabilities are always going to be values between 0 and 1. Probabilities can be changed into percentage. What's the chances of you passing the class? Stuff like that. As opposed to, somebody saying, oh, I'm going to give it 110%. That's what you think. Because 110% is a value that's bigger than 1. It doesn't fall under a probability or percentage. I mean, you can imagine that, but go ahead. Okay? Any questions? All right. There's one more special application. It's so special, I guess, that they had its own section, and that's the surface area. So, wait, before we talk about surface area, there's this really one cool thing that I wanted to show you guys. And for some of the honors people, if you don't know what you're going to do for your honors project, this might be one of them. We'll see. No, I don't think this is an honors project. No, maybe it's an extra credit project. I don't know. Remember the ERF function that I talked about? This integral doesn't have a nice closed form that we can use. So eventually they defined this ERF function. But in statistics, people really needed to know this integral so that they can work with this the bell-shaped curve. So when they're doing and forming statistics as a subject, it turned out that this function kept on popping up a lot, e to the negative x squared, and then turns out that it's important because of ideas behind probability, where the density function has to be equal to 1. That they would really be interested in finding out what this is equal to. So they didn't really know how to do this, right? So they found a little trick when they studied polar coordinates. And so they call this something, let's just call it I for integral. I don't know. We want to find out what this is equal to. And so what they did was they kind of, what? Oh, yeah. That's true. Negative x squared. Yeah, if you were to plot that, you see this curve. Now, because this curve has a height of 1, already the area under the curve is going to be bigger than 1. So we want the area under the curve to actually be equal to 1. So people are interested in finding out what this is equal to. And nowadays, we could just punch it into Wolfram alpha and then we get a value. But I think it was interesting back in the day how a trick in polar coordinates can help us take care of this. So what they did was they squared both sides. So this is like the trick to this proof. They think about squaring both sides. And now they furthermore took advantage of some properties of the integral where you have dummy variables. And the idea behind a dummy variable is that when you take an integral, especially a definite integral, and you evaluate it, you could change the variables to whatever you want. I mean, we can start off by calling this x, but we can also call it something else, or z, or t, or lambda, or alpha, or call it whatever you want. But it seems kind of nice if we think about calling it x and y. So now that we have a couple of integrals that are split up like this, we can think about merging it into one integral. Like maybe putting this inside. Let's see how that would look like. Well, let me just skip a couple steps here. We're going to put this inside. And then it'll look like a double integral. So we put this inside there, and then we'll have this integral inside, and then this would be something that you can put inside of that integral. So we put integrals, a couple of things inside each other. And then now we have this. Okay, fine. Now the limits say that we're going to go from minus infinity to infinity in x and minus infinity to infinity in y. So we're essentially looking at the whole R2. Right? That's our domain, R2. And then one of the things that I do notice is there's an x squared plus y squared in there. So sometimes when you see an x squared plus y squared, you might start leaning towards trying to do things in polar coordinates. So that's what we're going to do. We're going to try to change it into polar coordinates. Which means, in terms of trying to figure out how to map out the whole xy plane in polar coordinates, what can we think about? we can think about letting r go from 0 to infinity. And then if r, the radial distance, goes from 0 all the way off to infinity, and then let's let theta spin around, then we can capture the whole xy plane, right? And we only have to go to 2 pi. So this will capture all of the xy plane. Okay? How's that going to look? Now our integral changed to go from 0 to infinity of e to the negative r squared. X squared plus y squared is r squared. Factor out negative sign. Not only that, the dx dy changes into r dr from 0 to infinity, d theta from 0 to 2 pi. Now this is an integral that you should be able to do. You expect Calc 1 students to be able to do this integral. It's just a u substitution. U is equal to negative x squared, negative r squared. Right? And then you have the integral from 0 to 2 pi of d theta, which you can take out separately. So this is 2 pi minus 0. And then this is whatever that is. So with the u substitution, and then, you know, the improper integral rules, let b go off to infinity and stuff like that. So we'll skip over that part. But let's say you did that, you would have the integral of e to the u du (0 to minus infinity), and then get extra negative 1/2 out here, something like that. So if you put minus infinity, that limit's going to go to 0. And then if you put 0, e to the u is 1. So that's actually just a positive 1/2. So this whole thing is equal to pi. Oh, that's kind of weird. What's equal to pi? The square of the integral is equal to pi, which means the integral itself must equal the square root of pi. Pretty cool, huh? Only if you're a math person. It's all right if you don't think it's cool. I think it's cool. Okay? So that's a nice little trick for being able to exploit that extra r that comes in when you do the change of variables. All right. So anyways, if you take this and you divide by pi, you get it to equal 1. Here's your normal distribution. Well, not quite. There's still some other stuff happening up there. Anyways, let's move on. Going on a little tangent. So now let's talk about surface area. Again, we can consider this another application, or in the book it's its own section. I suppose I could just give you the formula, right? That would be easy. Let me at least summarize the sketch of the graph or the proof. Since we have some of the tools already, not that, I don't know if you guys remember. It's one of those things where somebody asks, is that going to be important? I said, nah, it's not really. And then it comes up in a quiz. And so we'll start with our usual drawing of stuff, and then say you want to find the surface area in some region. I was tempted to draw a rectangle, but you don't have to. It doesn't have to be rectangular, and so you can imagine this being projected up on them. So you're looking at this surface over here and trying to find that surface area directly above that. And like we've been doing in calculus, we would break this up into little sub-pieces and estimate. So imagine cutting this up into little squares, and the easiest squares to cut it up with is just along the x and along the y. And so what we're going to do, or attempt to do, is we're going to cut this up the same way. Into little squares. Well, they're not really squares, but if we cut them small enough, we can find the area of those squares, because we can find areas of squares and rectangles, right? So although this is actually smooth, if you cut a small enough piece, it looks like it's flat, kind of like the Earth, right? People thought the Earth was flat because where they lived looked like it was all flat. But when you zoom out far enough, it's actually curved. So that's the same idea. And the way we're going to do that is we're going to take a look at just one little piece. I drew my rectangle incorrectly there. Yeah. You see? I don't know if you can see. Let's blow it up. So the rectangle I was trying to draw, that's kind of like a vector. Right? Maybe it has a length of delta x and delta y. Let's see, this is y, this is x. So that's a zoomed out version of that. What we're going to do is we're going to project this up on the xy plane, or on the surface, and then we're going to see kind of like a similar picture. Yeah. So let's see, this is that special point over here, and your surface, let's draw the surface in red. Too many strokes. That's your surface. What we're going to want to do is find a couple of vectors that's tangent to that surface. Now, if I recall correctly, that was a quiz question. Well, let's take a look at those tangent vectors. Let's take a look at this first tangent vector. This is going along the y, and it's not moving in the x. So I'm kind of seeing this as 0 in the x direction. And remember, if you move along the y by 1 unit, you're going to move up along the z by how many units? Slope f what? F or something. It's a partial derivative. Slope, partial derivative, f. We're going along the y, so I'm assuming it's in the y direction. And then similarly, you'll have your other tangent vector over here at 1, 0, fy. Yeah? Oh, the second one? Sure. Okay? Now, this doesn't have necessarily a length of 1, because remember, you can adjust the size of delta x and delta y to be smaller. And so this needs to be multiplied by delta x and delta y. Just scaled in the x and the y. All right? Now, I don't want the whole tangent plane necessarily, but I would be interested in finding out what this, because it's flat. I would be interested in finding this area. Hey, it looks like a parallelogram. Area of a parallelogram, we've done that before. How do you find the area of the parallelogram spanned by two vectors? The magnitude of the cross product. Take the cross product, take the magnitude. And we seem to be out of time. So we'll keep you in suspense. We'll let you know what happens next time. It's like a cliffhanger. And you really, really, really want to know, don't you? What? Somebody said it already. Quiz tomorrow is on double integrals. It's on double integrals.